In the last lecture, we have seen how to calculate the force on a particular charge due to the another point charge. Also, we have seen that the electric field intensity of a particular point due to the electric field produced by point charges. Now, instead of considering the point charges, if we consider the line of charge, the surface of charge and the volume of charge, then how to calculate the electric field intensity, that we are going to see in this lecture. So, let us start the topic today, that is the calculation of the electric field intensity for the line charge, for the surface charge and for the volume of charge. So, here to calculate the electric field intensity, first we are considering the line charge density rho L, that is will be in coulombs per meter, and for the surface charge the charge density we are considering rho S, that is coulomb per meter square, and for the volume of charge we are considering the volume charge density rho V, which will be in coulomb per meter cube. Now, the density of the line charge and the surface charge and the volume charge is considered symmetric. So, from that we will consider, or we will calculate the total charge, and then we are going to use our known equations, that is the calculation to calculate the electric field intensity, the equation which we have derived in the last class. So, here if we have considered the line charge, the surface charge or the volume charge, then the charge element for a line charge we can consider dq, or for the surface charge also, and for the volume of charge we can consider the elemental charge, that is dq. Now suppose we have for the small length dl, in case of line charge, small length dl, we have the charge, that is dq. Now we can write dq equals to what? The charge density, because the density of the charge is symmetric. So dq, the charge enclosed by the length dl, is rho L into dl. So as we got the expression dq, so from that we can get the total line charge q, which will be equals to the line integral of rho L dl. Similarly, for the case of surface charge, if we consider a small area ds, on that surface area, if we consider the charge density is dq, then the total the charge inside the ds is equals to rho s into ds, because rho s is the surface charge density into the surface area, we will get the total charge inside this ds area. So now the total surface charge q will be equals to surface integral of rho s ds. So similarly we can find out the charge, total charge density for the volume of charge, that is q equals to rho v, volume integral of rho v dv. Now we know for the point charge the electric field intensity equation E equals to q by 4 pi epsilon naught r square into AR, that we have seen in the last class. Now that equation we are going to use here to calculate the electric field intensity for the line charge, for the surface of charge, for the volume of charge. Here you can see that for the point charge this is the equation. Now in the case of line charge, that q we have calculated. So if we have calculated the q, then we can replace this q by the expression, that you can see that this expression 2.1 we can use. So here the E equals to line integral of rho L dl by 4 pi epsilon naught r square AR. Similarly, for the surface charge, the electric field intensity E will be equals to surface integral of rho s ds by 4 pi epsilon naught r square AR. And for the volume of charge, the same way we can calculate E equals to volume integral of rho v dv by 4 pi epsilon naught r square AR. Now let us see how to calculate the electric field intensity for the line charge for first. So here we are going to use the diagram here in this equation. The you can see the diagram, that is in Cartesian coordinate system. Here for the line charge we are going to calculate the electric field intensity at the point whose coordinate is given by x, y and z. So in this Cartesian coordinate system, the line of charge is presented, or it is uniformly distributed along the z axis, and its density is given rho l. So to calculate the electric field intensity at this point, and the coordinate of this point is x, y, z, first what we are going to do is we need to consider a small length dl, and its coordinate is given by 0, 0, z prime. Now the next point is to calculate the charge, and in this dl length we want to find out, that is dq we have considered. So the charge dq can be written as rho l into dl, but here dl is a very small length and its coordinate is z prime, so we can write that is dq equals to rho l dl or rho l dz prime. So here the q charge, total charge in the line, q will be equals to the line integral, and its limit is a to b rho l into dz prime. Now we said earlier that we want to find out the electric field intensity at the point P, say P here, and its coordinate is x, y, z. So what we need to do is, now we need to draw a straight line from this coordinate 0, 0, z prime to the point x, y, z. That means we need to connect the dl point and to the point where we are going to calculate the electric field intensity. So this distance we are considering a capital R. So now first we want to find out the the electric field intensity E. We can write equals to, you see that the line integral of a to b and rho l dz prime by 4 pi epsilon naught r square ar. Same equation, only the r is replaced by this integration of a to b rho l dz prime. So this is the expression of the electric field for a line charge, and which is limited to a to b. Now we are going to derive that expression of the electric field E in different form. Now why we are deriving this equation in different form, we will understand at the end of the lecture. So let us consider that from the figure we can write dl equals to dz prime, because you know here you see that this is the expression. Here dl is very small, so its coordinate is z prime. So from that we have the expression, that is dz prime. So here, so dl equals to dz prime. Now we can calculate r vector. R vector is the distance vector from the coordinate of the position where we want to find out the electric field intensity, that is x, y, z, and the position of the dl point, that is on the z axis, that is 0, 0, z prime. So that to calculate this one, again you can see that here the expression x, y, z, and here 0, 0, z prime. So this minus this point will give us the expression of r. So here we can see that x, y, z minus that 0, 0, z prime. So x minus 0 ax plus y minus 0 ay plus z minus z prime az. Now from that we can find out x ax plus y ay plus z minus z prime az. Now you can see that again, if we move to the expression here, you can see that x ax means along the x direction, amplitude x in the direction of unit vector ax, then we are moving in this y direction, so it is y ay. So actually we are getting x ax plus y ay, that means we are getting the radial distance along the on this xy plane. So what we can write is that this x ax plus y ay can be written as r ar. If you remember the cylindrical coordinate system, from that we can find out the r. So here small r ar equals to x a plus y ay. Now we can write the r again, r equals capital R equals to small r ar plus z minus z prime az. Now as we have the capital R, the vector, then we can calculate the magnitude of r, that is mod of vector r root over of here r square plus z minus z prime into az square. So AR dot AR will be 1. So here we will get r square plus z minus z prime square. So it is the magnitude of r we got. And also we know that this r, small r, we can find out from this expression r equals to root over of x square plus y square. Now our aim is to find out the unit vector AR. AR equals to the vector r by the mod of vector r. So you see that the vector r is represented by this one RAR. So RAR plus z minus z prime az, and this r is mod of r means we are getting this one, that is r square plus z minus z prime square to the power half, that means root over of r square plus z minus z prime square. So now we got the AR. So now we can find out AR by r square. So here AR by r square means r divided by r square into mod of r, so r by r cube. So here the equation calculation is simple. R will be same, RAR plus z minus z prime az divided by this r we know, root over of r square plus z minus z prime square. So from that we are getting n cube means r square plus z minus z prime square whole to the power 3 by 2. Now we are going to substitute this expression into the equation 2.9. Here you can see that 2.9 here. So this AR by r square is replaced by the expression which we have calculated, which we have seen here, that is the expression AR by r square that is replaced in the equation here. So we will get E equals to integration of a to b rho l 4 pi epsilon naught. AR by r square will be replaced by the expression here, this one, then we will get AR. So ultimately what we are getting is E equals to rho l by 4 pi epsilon naught. This, all these terms are constant, so this is taken outside the integration. Integration of a to b r AR, you see that r AR plus z minus z prime az divided by r square plus z minus z prime square whole to the power 3 by 2 and dz prime. Now instead of considering the limit a to b, if we consider the limit alpha 1 and alpha 2, so what will happen, that we are going to see. So we can write, so here you see that here the expression, you see that this is, instead of considering a to b, here we have drawn the r, that is the perpendicular distance from the z axis to the point where we want to find out the electric field intensity. So this angle is alpha 1, that is replacing a, and alpha 2 is replacing b. So here we have again we know that r, this r equals to mod of r, that is equals to root over of r square plus z minus z prime square. That can be written as r sec alpha. Now how we are calculating this, we are replacing this expression by r sec alpha. You see that we have taken this triangle that we can get here. This is the r, this is z, this is z prime, this is capital R, and this angle is alpha. That triangle we are taken in that expression in this page. Here you see that this is r, z minus z, and here z prime r, this is the angle alpha. Now here you see that if we consider this r by capital R here, then it will be cos alpha. From that we can get the capital R equals to r sec alpha. Similarly, here again we have this small r equals to, from that expression also, small r by capital R equals to cos alpha. So small r equals to capital R cos alpha. Now again you can see that this expression, how we are getting this distance we can get is z minus z prime. So z minus z prime by this capital R, that we will get equals to sin alpha. So from that z minus z prime equals to capital R sin alpha. From this equation we will get. Now again you consider, if we consider z prime, z prime means what? The position where the dl is present. So z prime equals to, you see that again, z prime equals to o to t. Here this is the t, this is the constant value ot. Again OT minus TZ prime. So here you see that TZ prime. If we take minus of this OT minus TZ prime, then we will get Z prime. This point we will get. So here we are getting Z prime equals to OT minus TZ prime. Now we have OT is same. Now TZ prime is nothing but this distance. So this TZ, that means this distance by this small r, from that we will get tan alpha. From that what we are getting, that Tz equals to r tan alpha. So here Tz equals to r tan alpha. So now if we take the derivative of this expression Z prime, so dz prime equals to, here OT is the constant value, so it will be 0, then the derivative of this expression minus r sec square alpha d alpha. So now putting the expression of this small r, this z minus z prime, all these expression in equation 2.10, we are going to get one expression that we will see. Here you see that E equals to rho L by 4 pi epsilon naught, that is constant. You see that this is the constant, and now the limit is changed because we have considered now the limit alpha 1 to alpha 2. So here alpha 1 to alpha 2, alpha 1 to alpha 2. Now you see that small r means r cos alpha. So r, capital R cos alpha into AR, capital R cos alpha AR. Sin Z minus Z prime means capital R sin alpha AZ, capital R sin alpha AZ. Now this R square plus Z minus Z prime square whole to the power 3 by 2, from that we can find out that is R cube sec cube alpha, r cube sec cube alpha, because it is, if we consider this is root over means half, then if you multiply this by cube, then 3 by 2, that will be r cube by sec cube alpha, and that you will get from this is the expression. So now this expression we got. Now you see that the expression dz prime, so here dz prime is minus r sec square alpha d alpha. So here we have written this minus r sec square alpha d alpha. So minus taken outside, so minus of rho L by 4 pi epsilon naught integration alpha 1 to alpha 2, capital R cos alpha AR, because R is taken common, plus sin alpha AZ, divided by here r cube, so cancel out. So here you will get r square sec square alpha sec cube alpha, so we will get sec alpha and d alpha. So this is the expression we got. Now you see that in this expression, if we consider only r into r sec alpha, r into r sec alpha, so r sec alpha, you see that r sec alpha, this r sec alpha means capital R. So here r sec alpha will be equals to capital R. So capital R cancelled out, and this r is taken outside the integration, because r is the distance or the perpendicular distance from the z axis of the point of our interest, where we are going to find out the electric field intensity. So that r is taken outside, that is constant. So r is taken outside. Now you see that the integration alpha 1 to alpha 2, we have cos alpha AR d alpha, if you multiply here, plus again integration alpha 1 to alpha 2 sin alpha AZ d alpha. Now you see that if we take the integration of this cos alpha d alpha and sin alpha d alpha, we will get the answer. So here E equals to minus of rho L by 4 pi epsilon naught R, and here cos alpha, if we take the integration sin alpha, limit is alpha 2 alpha 1 AR, plus sin alpha integration, if you take this minus cos alpha, and the limit is alpha 2 alpha 1 and AZ. So from that we are getting, and putting the value of this limit alpha 2 alpha 1, we are getting the expression. You see that rho L 4 pi epsilon naught R. Here you see that this is the first sin alpha 2 minus sin alpha 1 minus of cos alpha 2 minus cos alpha 1, but minus if we take in outside, then it will be plus. So here we will get this expression, that is the sin alpha 1 minus sin alpha 2 AR plus cos alpha 2 minus cos alpha 1 AZ. Now this is the expression of the electric field for this limited line charge and electric field E at the point whose coordinate is x, y, z. Now we are going to consider a special case. That is why we derived all this equation in this form. So the case is that we are now considering the electric line, that is the line of charge which is infinite, line of charge infinite, and also it is along the z axis. Now if it is infinite and along the z axis, then the point B will be at the coordinate 0 0 infinite, and point A will be at 0 0 minus infinite. Now how we are getting that? We can see from the diagram. You can see that here, if we take B, this infinite line of charge, so B will be at infinite, so in this direction, so x is 0, y is 0, and z is infinite. Similarly, A will be equals to x is 0, y is 0, and z is minus infinity. In this way, we can find out the expression, that is B equals to at 0 0 infinite, A equals to 0 0 minus infinite. Now we can find out the alpha 1, that is pi by 2 90 degree, and alpha 2 equals to minus pi by 2. So now how we are calculating this alpha 1 equals to pi by 2, that also we can find out from the diagram. Again we are going to see the diagram, and you see that this alpha 1, from for that we are getting that from the axis anti-clockwise direction. So here you see that, so here if we move the A in this direction, then alpha will increase, and if A is at infinite, then is A will be parallel to this Z coordinate. So this R and this A will be at 90 degree. Alpha 1 will be equals to pi by 2. So here you see that we are moving in the anti-clockwise direction. Similarly, if we move the point B in this direction, then one point we will get that it is clockwise direction. Also we will get B first, alpha 2 will decrease 0, then it will increase in the negative direction. So and when the B reaches the infinite, then again it is the angle 90, but it is clockwise direction we are taking, it is minus uh, pi by 2, that is minus 90 degree. So here that is how we have got alpha 1 and alpha 2. Now if we put the expression of alpha 1 is 90 degree and alpha 2 is minus 90 degree, from that sin 90 you know what is the value sin 90, 1. Here sin alpha 2, that is minus 90, that from that we can get 1. So here you will get that is minus 1. So here minus 1 plus 1, so 2 into AR, and here cos will be 0. So 2 and 4 so cancel out. So what we are getting that E equals to rho L by 2 pi epsilon naught R into AR. Now this is the expression of the electric field intensity at the point whose coordinate is xyz for infinite line charge. And interestingly, from this equation we can see that this electric field intensity is not dependent on the length of the line charge or the length of the line of charge, because you see that rho L is constant, 2 pi epsilon naught is constant. So E is only dependent on the value of R, which is the perpendicular distance from the Z axis to the point of our interest where we are going to find out the electric field intensity. So it is very important equation. From this equation, the information what we are going to get is that the E is dependent on small r, not on the length of the line of the infinite line which is present in the along the z axis. Okay, so that is all for today's class, students. In the next class we will see the another application of the Coulomb's law to calculate the electric field intensity for the surface charge density. Thank you very much.